Okay, let's unpack this. Welcome to the deep dive. Today, we are tackling a mission that is, absolutely critical to human civilization. The engineering, the planning, and the science behind getting clean water from its source all the way to your tap.
Exactly. And this isn't just a casual chat. This is a really comprehensive, exam-focused deep dive into the OEN 351 syllabus. That's drinking water supply and treatment. We know that you, as a student, are aiming for mastery here. So our goal is to extract every single definition, formula, and maybe most importantly, those complex technical comparisons you're going to need to really excel.
Absolutely. And our source material for this is just exceptional. It's a comprehensive set of technical notes, and they're so meticulously compiled and organized, it really seems like they are put together for this exact purpose, to simplify a pretty demanding engineering course. So we should definitely acknowledge the individual associated with this compilation, Dr. Aaron Kumar, for providing the foundation that's going to let us move through all 5 of these core units with real precision.
Our mission today is pretty rigorous. We're going to start with raw water planning, that's Unit 1, and then conveyance in Unit 2. Then we'll move through the entire really intricate treatment train units 3 and 4, and we'll finish up by summarizing the challenges in distribution, which is Unit 5. We're definitely going to slow down on the calculations and the essential trade-offs that separate a superficial understanding from genuine engineering insight.
Right, let's start at the very beginning then. Unit 1, the concept itself, the public water supply system.
The definition, and this is a good one to remember, is supplying safe and wholesome water from large water resources by treating it and then bringing it in an efficient manner to the public.
That definition really covers a lot of ground. It's economics, chemistry, hydraulics, all in one sentence.
It is, and its history shows this clear evolution of priorities. Early civilizations, think about those along the Nile or the Indus, they understood that water quantity was just paramount for survival, for agriculture.
Right.
But the focus on quality, that came much, much later. And if you want a kind of surprising historical nugget for your exam, you can look back to Sanskrit literature. There's the Sushruta Samhita from around 2000 BC, and it already mentioned these rudimentary treatment methods, things like storing water in copper vessels, exposing it to sunlight, and filtering it through charcoal or sand.
That's ancient knowledge. But the modern, the rigorous approach to quality, that was really cemented by disaster, wasn't it?
Yeah.
We always talk about Dr. John Snow in London back in 1849. He meticulously mapped where the sick people were and established that direct link between contaminated water from the Broad Street pump and that just devastating cholera outbreak. I think it killed over 14,000 people.
It did, and that one event really cemented the necessity for a protected, planned water supply. And the impact of controlled quality is, it's undeniable. We have some striking data, like a World Health Organization report from 1963 on morbidity decrease in Uttar Pradesh, India. It was achieved simply by introducing free drinking water. Cholera cases dropped 74.1%, and typhoid cases went down by 63.6%.
It's huge. This global recognition eventually led to the UN declaring health for all by the year 2000 AD, back in 1977. And that really emphasized safe water access as a basic right.
So if the necessity is that clear, then the goal has to be defined, and that goal is wholesome water.
Yeah.
So what are the essential requirements? It's got to be more than just being free of pathogens.
Oh, absolutely. That's a critical exam definition right there. Wholesome water must be free from harmful bacteria, yes, but it also has these aesthetic criteria. It must be colorless, sparkling, tasty, cool, and odor-free. And from an engineering perspective, and this is key, it must not corrode pipes. That means it needs enough dissolved oxygen or TEX-DOA, but it has to be free from aggressive compounds like carbonic acid.
Hold on, I remember the detail here that's interesting.
Yeah.
If water is chemically pure, like just text, it's actually not wholesome, is it? Why is that technically? That is absolutely correct, and it's a great distinction to make for an exam. Chemically pure water, water that's devoid of all dissolved solids, is extremely aggressive. It wants to dissolve things, so it's highly corrosive to pipes. But more importantly, wholesome water must contain small, requisite quantities of minerals, things like calcium, magnesium, iron, and zinc. These are actually essential for human health. Potable water is the broader term. It just means it's safe and agreeable. Wholesome water meets both the safety and the necessary mineral requirements.
Got it. So once we understand the goal, we have to move to the planning of the water supply system. An engineer starting a new project has to juggle, so many conflicting constraints. What are the top 8 factors?
You should definitely memorize this list for any short answer questions.
Fire.
The financial aspect, that's always first, then accurate population growth projections, assessing the quality and quantity of the raw water you have available, determining the rate of consumption.
Okay, so that's 4.
Right. Then understanding the usage of water, is it industrial or domestic? A thorough sanitary survey of the area, source selection, and finally, how you're going to manage all the service connections.
And it's not a one-person job, obviously. The notes really emphasize the different agencies that are involved in this kind of coordinated planning. Can we clarify the roles of a few key ones?
Certainly. Understanding the organizational context is important. You have NERI, the National Environmental Engineering Research Institute. They focus on research, surveys, and design standards. Then there's CPHEEO, which is the Central Public Health and Environmental Engineering Organization. They formulate the central government schemes. And then CGWD and GSI, that's the Central Groundwater Board and the Geological Survey of India. They're the specialists who assess and certify groundwater resources. It ensures a consistent, centralized approach.
Okay, that makes sense. Now let's talk about the timescale. Planning requires setting a design period. That's the number of years for which the waterworks are designed to meet future demand. And the notes say it's typically between 22 and 30 years.
But here's the nuance, and this is what makes it a great exam topic. Not all the components are designed for the same lifespan, and that's because the difficulty of replacing them varies so wildly. This table of data is crucial.
All right, let's look at the extremes. What component has the longest design life?
That would be the things that are nearly impossible or just prohibitively expensive to replace. They get the longest lifespan, typically 50 years. And that category really includes storage dams. I mean, once you build a dam, you don't just replace it. Then you have intermediate components, designed for 30 years. These are the major permanent buried infrastructure, things like intake towers, the main pipe connections, and the overall distribution system.
And what about the shortest life components, the ones designed for just 15 years?
Those are your mechanical, electrical, or chemical parts that become obsolete pretty quickly or just require frequent maintenance. So that's things like pumping electrical works, specialized treatment units, and clear water storage units. The engineering logic here is actually quite simple. Designed for the longest possible life for the things that are hardest to replace, and the shortest practical life for things that have high obsolescence or just a lot of wear and tear.
Right, and the single most impactful variable in sizing any of this is the future population. You have to predict growth based on birth rates, death rates, migration, all of it. And since we can't use a crystal ball, we use forecasting methods.
Exactly. Let's start with the 3 most important mathematical methods and really focus on where you would apply each one. First is the arithmetical increase method. This assumes a constant quantity of growth. So the rate of growth, CMC, stays the same each decade. It's really only suitable for large old cities where growth is kind of stabilized. The formula is text P plus NC dot C1.
Okay, constant growth amount. What's next?
Next is the geometrical increase method. This one assumes a constant percentage growth rate, the geometric mean, or IGOS. Because it projects rapidly increasing populations, it's best for new industrial towns or cities that are in a rapid development phase. The formula there is text TN 1 plus text IG 110.
And the third?
The third is the incremental increase method. And this one is the most practical modification for your average-sized developing towns because it accounts for a growth rate that is itself increasing. It incorporates the average incremental increase, which we call Y, as sort of correction factor. The formula is text PN plus NEP plus NM plus NN plus YYS.
To really drive home the engineering consequence of picking the wrong method, let's quickly run through the example from the notes. It uses census data from 1940 to 1970 and asks us to project the population for the year 2000.
Okay. Using that data, the average arithmetic increase, C or X, comes out to 433 per decade. The average incremental increase, Y, is 750 per decade. We're projecting 3 decades, so N3, from the 1970 population, which was 22,500.
Right. So calculation 1, the simpler arithmetical method, that gives us 22,500 plus 3 times 400, 833, 3. That results in a forecast of 36,999.
Now, for calculation 2, the more nuanced incremental increase method. That gives us 22,500 plus 3 times 400, 833 plus $22,500 plus 14,499 plus $4,500, which gives us a forecast of 41,499.
Just look at that difference. That's 4,500 people As an engineer, what are the immediate practical safety and financial implications if you choose the arithmetical method when the incremental one was actually more appropriate?
The implication is massive, and this is exactly the kind of insight that examiners are looking for. If you underforecast by 4,500 people over 30 years, you undersize your primary pipes, your pumps, your treatment units, everything. Critically, your main distribution pipes will not be able to deliver the required pressure and flow for peak demand, especially fire demand. You'll get low pressure all over the system during daily peaks, which leads to customer complaints and, far worse, a complete failure to meet fire suppression needs. An undersized system designed for 37,000 people that rapidly grows to over 41,000 becomes a functional failure. It'll require immediate, unplanned capital expenditure to replace the core infrastructure well before that intended 30-year design period is even close to being over.
So you turn a 30-year asset into a 10-year failure. That's why these formulas are so foundational.
Now, let's try to quantify that demand. The general thumb rule for the total daily requirement is 270 liters per capita per day, or LPCD. But that 270 breaks down into 6 distinct categories, and we need to detail them.
The largest, of course, is domestic water demand. The standard IS 1172-1963 sets the norm for a small Indian city at 135-pound PCD. And this number just skyrockets in metros or developed countries up to 350-pound PCD sometimes. And if we look at that 135-pound PCD breakdown, it's a fascinating insight into our consumption habits. Bathing and laundry, that's the biggest chunk at 55-pound PCD, and just flushing toilets accounts for 30-pound PCD.
And understanding that breakdown is so key for water conservation policy. Next, we have industrial demand, which typically accounts for about 20 to 25% of the total consumption. These requirements can be extremely high for certain sectors. You should cite examples like paper manufacturing, which consumes 200 to 400 kiloliters of water per ton of paper, or distilleries, requiring 122 to 170 kiloliters per kiloliter of product.
Then there's institution and commercial demand. Again, usage varies a lot based on the facility. Offices need 45 to 90 pounds DCD, while a hotel demands 180 liters per bed. And we also have to allocate for demand for public use, which covers things like street washing and parks. This is usually just a blanket provision of 5% of the total consumption.
And now for the heavy hitters, literally. The fifth demand type, fire demand, is absolutely crucial because it governs the maximum size of your pipes and the required pressure rating. It dictates the system's ability to handle that extreme, instantaneous flow you need during a large urban fire.
Which means we have to memorize the empirical formulas. In these, Q is the required flow in liters per minute, and P is the population in thousands.
Right. First, there's Küchling's formula. 2 equals 382 times. Then the National Board of Fire Underwriters formula, which is a bit more complex. Q equals 637 times 1.01 times Schwarzschild.
And is there a simpler standard to use?
Yes, the IS 9668 1990 standard provides a practical benchmark. It's 1Q 1800 text La Nina for every 50,000 in population, up to a limit of 300,000 people.
Got it. And finally, the unavoidable fact, losses and wastes.
Yes. An allowance of about 15% of the total quantity is standardly built into the design budget to account for defective joints, illegal connections, wastage from open taps, and just general system leakage.
That 15% allowance really is an engineering compromise, isn't it? It's acknowledging that perfect infrastructure is basically impossible. Let's quickly review the factors affecting per capita demand. Beyond just the size of the city and industry, pressure plays a huge role.
It does. Higher pressure in the distribution system leads to more leakage and increased, often wasteful, usage by consumers. And of course, climate. A hot climate increases bathing and lawn watering demand, but a very cold climate can also increase demand if people leave taps running to prevent their pipes from freezing.
We have to end this unit by quantifying the variations in demand, because these are what drive the peak design requirements.
Right. Seasonal variation is maximum in the summer, maybe 15% above average. The maximum daily consumption is usually about 180% of the average daily figure. But for sizing pumps and local distribution pipes, we use the factor that peak hourly consumption on the maximum day can be up to 2.7 times the average daily demand. That 2.7 multiplier is your key design stress factor.
Okay, let's move from planning to actually sourcing and moving the water. Starting with the global perspective, it's kind of shocking that only a tiny 0.56% of the Earth's total water is available for us to use.
It is shocking. Most of it, 97.3%, is in saline oceans, and another 2.14% is locked up in ice caps. That tiny fraction we can use is sustained by the hydrological cycle. That's the continuous process of evaporation, transpiration, precipitation, runoff, infiltration, all of it. It's nature's purification and distribution engine.
And the sources are basically classified into surface sources like streams, rivers, lakes, and subsurface sources, which is groundwater. The trade-off here is often quantity versus quality.
Exactly. Surface water gives you high quantity, but the quality is challenging. River quality, for instance, just plummets during monsoon because of high turbidity. And impounding reservoirs, while great for dry season storage, they suffer from biological issues, algae, weed growth. They require specific pre-treatment steps like aeration and chlorination to deal with the tastes and odors that these organisms generate.
Groundwater, on the other hand, is naturally filtered, so it's biologically pure, but it often has a high dissolved salt content, which leads to hardness. How do we actually tap into that?
We use structures like infiltration galleries. These are horizontal tunnels, often built parallel to rivers, tapping into the water table near the bank. They're pretty effective, yielding up to 15,000 liters per day per meter. Or we can use infiltration wells, which are sunk in a series and then connected to a central collection point called a jack well for centralized pumping. And then, of course, you have springs, which are just points where groundwater reappears at the surface.
Okay, so once you have the source, you need the intake structure. This is the gateway. Its function is the safe withdrawal of water from the source to get it to the treatment plant. Location has to be key here. What are the critical factors?
For the exam, you should know these 7 points. It must be near the treatment plant to reduce conveyance cost. It has to be in the purer zone, so upstream of any sewage discharge. It needs to be able to draw water even in the driest season, be protected from floods and strong currents, and be away from navigation channels. And importantly, it has to be located where future expansion is possible.
Let's contrast the two main types of intake towers, which are used when the water level fluctuates a lot, like in a big reservoir.
Right. You have the wet intake tower, also called a jack well. It's essentially a continuous vertical shaft where the water level inside matches the source level. Pipes draw water through screened openings at various depths. Then you have the dry intake tower. Here, the water is drawn directly into the withdrawal pipe system, so if the gates are closed, the tower itself remains empty. This requires a much heavier, more robust structure to withstand the external water pressure.
So the structural cost is higher, but I imagine maintenance is easier.
Exactly. The access for maintenance is much easier in a dry tower.
Okay, once withdrawn, the water has to be conveyed. We use either gravity conduits, like open channels where the flow is driven by slope, or pressure conduits, which are pipes where the water is under pressure.
And a key engineering detail about gravity flow in aqueducts: they should not be designed to run full under pressure. If pressure builds up, it causes tensile stress and leakage, and that can potentially compromise the whole structural integrity of the channel.
Speaking of integrity, the requirements of pipe material are a great topic for a short answer. They have to withstand internal pressure, external soil load, temperature stress, be durable, non-reactive with the water, and minimize frictional head loss.
Now let's do a critical trade-off analysis of the main pipe materials. This is crucial for exam success because it goes beyond just simple pros and cons and gets into life cycle cost.
Okay, let's start with the classic: cast iron, CI, pipes.
CI is strong, it's durable, it boasts a 100-year life. The installation cost is moderate. However, and this is the major engineering problem, its tendency toward tuberculation, that's the formation of rust nodules inside the pipe. This drastically increases the pipe's roughness, which leads to severe head loss and a reduced carrying capacity over time, sometimes by 50% or even more. It's also very heavy and just becomes uneconomical above a 1,200 millimeter diameter.
Okay, so compare that to steel pipes. They are cheaper initially, they're flexible, and they come in long lengths, so they resist high internal pressure.
But the life cycle cost is higher. Steel is highly susceptible to both external and internal corrosion. It requires extensive protective linings and high maintenance costs. Repairs are also more time-consuming during a breakdown. An engineer chooses steel when high internal pressure or maybe seismic activity, where you need that flexibility, is the main constraint, and they have to accept that higher maintenance burden.
And finally, what about concrete pipes? Reinforced or prestressed?
Concrete is incredibly durable, up to 75 years, and unlike cast iron, it has a smooth interior that does not rust or tuberculate. That means its friction factor stays high, which minimizes operational energy costs from pumping. But the trade-off is obvious. They're extremely heavy. That makes transport and installation difficult, and repair is complex. An engineer would choose concrete for massive, non-pressurized gravity mains or long-distance aqueducts, where that long-term operational efficiency outweighs the initial difficulty of placement and repair.
Let's talk a bit more about pipe corrosion. What causes it, and what are the effects beyond just, a simple leak?
The causes include low pH, so acidic water, dissolved gases like TeX-CO2s and TeX-WO2, high salt content, and even stray electric currents from nearby infrastructure. The effect of tuberculation is often underestimated. It's not just a physical obstruction, it's a drastic increase in boundary layer friction. It significantly increases the required pumping head to deliver the same flow. That's a massive hidden operational cost. Prevention includes adjusting the water's pH, using protective linings like asphalt or cement mortar, and then very expensive solutions like cathodic protection.
And the forces on these pipes are incredible, but the most destructive transient force is water hammer. We should probably detail this.
Water hammer is the immense pressure surge caused by the sudden stopping or changing of water velocity. It usually happens when a pump stops or a valve is closed too quickly. All the kinetic energy of that moving column of water is suddenly converted into pressure energy, causing a wave that travels back and forth through the pipe. It can be incredibly destructive.
So what are the protection measures for that?
Engineers protect the system using specialized devices. Things like air chambers, which are vessels installed near pumps or valves that absorb the pressure surge by compressing air inside, or surge tanks, which are large vertical tanks that absorb or release water quickly during those pressure fluctuations. Designing the system to mitigate water hammer is absolutely essential to prevent catastrophic pipe bursts.
Okay, now to the local level, the distribution system. We need appurtenances to control flow, regulate pressure, and manage the system. Let's define the key valves.
First, you have sluice valves or gate valves. They're the most common. Their main function is isolation. They control flow and let you shut down sections of pipe for maintenance. They're placed strategically every 150 to 200 meters. Then you have check or reflux valves. They're an automatic device that prevents backflow. Basically a one-way street for water. Air valves are placed at high points or summits to release accumulated air that would otherwise create an airlock and block flow.
What about safety from overpressure?
That's a relief valve or a safety valve. It's an automatic release that opens if the pressure exceeds a safety limit, protecting the pipe from bursting. Then there are altitude valves used for elevated tanks. They automatically close when the tank is full. And finally, drain valves, or scour valves, located at low points and dead ends to allow flushing of stagnant water.
And finally, pumps. We noted that centrifugal pumps are the most widely used in water supply because they can handle varying flows and some silt.
That's true, but you have to know their limitations. Centrifugal pumps are best for moderate head and high discharge. They lose efficiency dramatically at very high heads. If you're drawing water from a very deep well, or you need exceptionally high pressure for fire protection, you might need a displacement or reciprocating pump. They're better suited for small discharge, but very high pressure.
The practical process of starting a centrifugal pump is called priming. Why is that so essential?
Priming just means filling the pump casing and the suction pipe entirely with water before you start it. A centrifugal pump works by creating negative pressure at the center of its impeller. If the casing is full of air, the impeller just spins the air. It can't generate enough negative pressure to draw the heavy water up, so priming ensures that the heavy water column can be moved.
Okay, that brings us to Unit 3, the core of purification. Conventional water treatment. What's the comprehensive objective here?
There are 8 core objectives. You want to remove objectionable color, taste, and odor, remove suspended and colloidal impurities, reduce hardness and corrosiveness, remove dissolved gases, and most importantly, remove pathogens to make the water safe.
And we have to remember the distinction between unit operations, the physical actions like screening and filtration, and unit processes,
Yes.
which are the chemical or biological reactions like coagulation and chlorination.
Exactly. And the standard treatment unit flow diagram is intake, then plain sedimentation, then coagulation and flocculation, then filtration, then disinfection, and finally to a clear water reservoir.
Let's start with aeration. What exactly is this process achieving?
It's primarily about gas transfer. It increases dissolved oxygen, the DO, which makes the water taste fresher. It strips out undesirable dissolved gases like hydrogen sulfide, H2S, and excess carbon dioxide, CO2. And getting rid of CO2 is great because it reduces corrosiveness. Chemically, it also oxidizes soluble iron and manganese into their insoluble forms, which can then be precipitated out and filtered.
And we need to know the different types of aerators.
Right. There are spray nozzles, which are highly efficient, sprinkling water under high pressure to maximize surface area. They can get up to 90% CO2 removal. Then you have simple cascade aerators where water just flows over steps. The removal efficiency is more moderate, maybe 60–70%. You can also use air diffusion, which is bubbling compressed air through the bottom of a tank. And trickling beds where water trickles down over coke or limestone, which is very effective for CO2 removal.
A key limitation to remember here. Aeration is not effective for removing chemical tastes and odors from, say, industrial compounds.
Correct. And if you remove too much CO2 too quickly, it might temporarily increase the water's corrosiveness until the pH stabilizes.
Okay, next is the chemical process of coagulation and flocculation. This is essential for removing those tiny, negatively charged colloidal particles that just won't settle out on their own.
Right. The purpose here is the destabilization of those particles so they can clump together or aggregate into large, heavy flock.
And this involves three critical stages. Rapid mixing in the flash mixer, where you add the coagulant, then gentle stirring in the flocculator to allow the flock to form, and finally, gravity settling in the sedimentation tank.
The industry standard coagulant is aluminum sulfate, or alum. It works by reacting with the natural bicarbonate alkalinity in the water to form an aluminum hydroxide flock. This reaction is highly pH dependent. It needs a range of 6.50 to 8.50. The typical dosage is about 10-30 milligl.
So what's the significant engineering downside of using alum?
Well, the reaction consumes alkalinity and produces CO2. This CO2 lowers the water's pH, which increases its corrosiveness. And that goes directly against one of our main goals of producing wholesome water. Furthermore, a byproduct, calcium sulfate, contributes to permanent hardness. So that's the major trade-off. You get great particle removal, but you might introduce corrosion and hardness issues that you have to deal with downstream.
And there are other coagulants like ferrous sulfate and lime, and these things called polyelectrolytes.
Yes, polyelectrolytes are high molecular weight polymers. They're often used as coagulant aids at very low dosages, maybe 1 ppm, to produce stronger, faster settling flock. And to determine the precise dose you need, balancing effectiveness against cost, we use the jar test apparatus. You test 6 different doses at the same time and observe which one gives you the best result. That's your optimum dosage.
Once flocculated, the water enters the sedimentation tank, where up to 90% of those suspended solids are physically removed by gravity. The design parameters here are critical for efficiency.
You need to know these exam figures cold. For coagulation-aided settling, the detention period is typically 2 to 2.5 hours. The overflow rate for horizontal flow is 30-40 cubic meters per square meter per day. And crucially, the velocity of flow must be kept extremely low, like 0.5 to 1.0 peter-seconds, to ensure that the settling flock isn't disturbed or carried out of the tank.
Okay, filtration is the final physical barrier. The theory of filtration is not just straining, is it? It involves 4 interwoven mechanisms.
Correct. You have mechanical straining, which is physical trapping, then sedimentation absorption, where colloidal particles adhere to the sand grains. There's also electrolytic action, which is electrostatic charges binding impurities. And the most complex one, biological action.
And that biological action is the foundation of the slow sand filter, right? The Schmutzdeck.
Exactly. The Schmutzdeck is a gelatinous biological film of algae, bacteria, and other microorganisms that develops on the surface of the sand. It actually biologically consumes and absorbs organic impurities.
The contrast between slow sand filters, SSF, and rapid sand filters, RSF, is a mandatory essay topic, so let's detail the trade-offs.
Okay, SSF relies on that biological Schmutzdeck, so it requires minimal pretreatment. The rate of filtration is extremely slow, 2.4 to 3.6 cubic meters per square meter per day. The media is very fine sand. It requires a massive area because of that slow rate. Cleaning is laborious. You have to manually scrape the top 2-3 centimeter layer, but its efficiency is excellent, 98-99% bacterial removal.
Okay, now for the RSF, it relies on physical straining and adsorption, which means it absolutely must have thorough pretreatment, like coagulation and sedimentation, to work properly.
The RSF is designed for speed and for water with higher turbidity. The rate of filtration is rapid, 100 to 150 cubic meters per square meter per day. The media is coarser sand. It requires a much smaller footprint. Cleaning is mechanized. It uses a process called backwashing with clean water and compressed air, which is fast, but it consumes a lot of your treated water, maybe 3-5%. And the RSF requires skilled supervision because of that mechanized system.
So the ultimate decision between SSF and RSF is usually dictated by land availability and the raw water quality.
That's right. SSF needs a massive area, and RSF is needed for high turbidity water.
Now for the most critical step, making the water safe. Disinfection. This is the process of killing infectious pathogens.
A good disinfectant has to be effective, fast, economical, non-toxic, and easily measured. But the single deciding factor is its ability to form a residual.
And that leads us directly to chlorination, the universally adopted method. Why does chlorine win out over alternatives like ozone, which is actually a stronger oxidant?
It's all about the residual. Chlorine provides a residual concentration that remains active in the distribution system. It neutralizes any recontamination that might occur from pipe leaks or breaks. Ozone is powerful, yes, but it leaves no residual, so you'd have to use a secondary disinfectant anyway, which just adds cost and complexity.
Okay, let's dive deep into the chlorination chemistry, because this is essential knowledge.
When chlorine gas, text distillate, dissolves in water, it hydrolyzes almost instantly. It forms hypochlorous acid, text HOCl, and hydrochloric acid, text H2col. The text HOCl is the primary disinfectant. It then dissociates into a hydrogen ion, text OCl, and a hypochlorite ion, text OCl. The collective term for text HOCl and text OCl is free available chlorine.
Okay, so here's the most important engineering insight regarding efficiency. What controls how effective that free available chlorine is?
pH control. This is the key. The undissociated form, text HOCl, is a significantly more powerful germ killer than the hypochlorite ion. It's about 80 times more effective because its small neutral structure lets it easily penetrate the cell walls of microorganisms. And the ratio of text HOCl is entirely dependent on pH. At a lower pH, say 6.5 to 7.5, you maximize the presence of the highly effective text OPL. If the pH rises above 8.5, most of your residual switches to the weaker text OCl, making disinfection much less effective.
Wow, so maintaining a slightly acidic to neutral pH is critical for plant operation.
Absolutely. And if the water contains ammonia, chlorine reacts to form chloramines. These are what we call combined residual chlorine. They're less powerful, but they provide a longer-lasting residual.
Okay, let's clarify the dosage types, especially the complex concept of breakpoint chlorination.
Right. Plain chlorination is simple. Just enough chlorine to get the required 0.2 milligl residual. Superchlorination is an excessive dose, maybe 10-15 milligl, used during epidemics, which then requires a second step called dechlorination. But breakpoint chlorination describes the process where you add chlorine to satisfy all the initial demands: organics, metals, ammonia. The curve has 4 phases.
Okay, break it down.
First, chlorine reacts with reducing agents like iron and is consumed immediately. Second, it reacts with ammonia to form chloramines, and the residual rises. Third, as the dose keeps rising, the excess chlorine starts destroying the chloramines and breaking down organics. The residual chlorine actually decreases here. And fourth, you reach the breakpoint. This is where all contaminant demand is satisfied. Any chlorine added beyond this point exists entirely as highly effective free residual chlorine. The goal is to operate just past this point.
And the points of chlorination are vital too: pre-chlorination, post-chlorination, and rechlorination. And the final design constraint is that you need 0.2 milligl of residual chlorine at the farthest point of the distribution system.
Correct.
All right, that brings us to Unit 4, Advanced Water Treatment. These are the processes designed to remove specific dissolved contaminants that conventional treatment might miss. Let's start with water softening.
Hardness is caused by multivalent cations, mainly calcium and magnesium ions. It's a huge economic issue. It wastes soap, causes scaling in pipes and boilers, makes fabrics rough. The maximum permissible limit is 600 millil as calcium carbonate.
And we distinguish between temporary hardness, which you can remove by boiling, and permanent hardness, which requires these advanced methods.
The 2 main technical methods are the lime soda process, which is chemical precipitation, and the zeolite process, which is ion exchange. The lime soda process uses lime and soda ash to precipitate the hardness ions. It's economical, but it generates very large volumes of chemical sludge that's difficult to dispose of.
Okay, and the zeolite process, that's ion exchange.
Right. Zeolite is a material that exchanges its non-hardness sodium ions for the objectionable calcium magnesium ions in the water. The beauty of zeolite is the regeneration. Once it's saturated with hardness ions, you just run a concentrated salt or brine solution through it. That forces the hardness ions off, making the zeolite reusable.
What are the pros and cons there?
Advantages are that hardness is reduced to basically 0. It's easy to operate, and there's no sludge. The main disadvantage is that it can't be used for turbid or acidic water. And because it's adding sodium, it can be an issue for people on low-sodium diets.
If softening is partial removal, then demineralization or deionization is near total removal of all ionic contaminants. You're aiming for water quality that's comparable to distilled water, but cheaper.
Exactly. The core principle uses 2 types of synthetic resins: cation resins and anion resins. The cations in the water exchange for hydrogen ions on the resin, and the anions exchange for hydroxide ions. The released H+ is OH that immediately combine to form high-purity water, H2O.
And the configuration of the beds is important here, distinguishing between two-bed and mixed-bed systems.
Right. In a 2-bed system, the water passes sequentially through a cation bed,
than an anion bed. It's effective, but there's a risk of what we call sodium leakage, where some sodium ions slip through and reduce the final purity.
Which brings us to the mixed bed system.
The mixed bed system mitigates that sodium leakage entirely by mixing the cation and anion resins together in a single column. This ensures the exchange happens hundreds of times through the entire depth of the column, yielding the highest possible water quality. The trade-off is regeneration. Separating those two types of resin for chemical flushing is far more complex than regenerating two separate tanks.
Okay, let's touch on adsorption. This is a physical phenomenon where molecules bind to a surface. It's used mainly for low concentrations of organics, taste, and odor.
And activated carbon is the champion here. It has an immense internal surface area. When the carbon becomes saturated, it has to be regenerated. For drinking water, this is usually done via thermal regeneration in a high-temperature oven, which basically burns off the absorbed organic compounds.
Now, for total dissolved solids and salt removal, membrane systems and desalination with reverse osmosis being the standard.
Right. RO is the act of forcing water through a semi-permeable membrane under high pressure, literally reversing the natural flow of osmosis. It's excellent because it rejects dissolved salts, organics, and microorganisms, but it requires extensive pre-treatment to prevent the membranes from getting clogged or fouled.
There are other membrane technologies too, like nanofiltration, NF.
Yes, NF is less fine than RO and is commonly used for water softening or as a pre-treatment step for RO. We also use electrical methods. Electrodialysis, ED, uses charged electrodes to pull ions through selective membranes. A superior version is electrodialysis reversal, EDR, which periodically flips the electrode polarity. This constant reversal prevents the buildup of mineral scale and fouling on the membranes, which dramatically improves its operational lifespan.
Okay, iron and manganese removal. These are common groundwater problems. Above 1 mg/L, you get a metallic taste, staining, and pipe incrustation.
The core treatment is oxidation. The most cost-effective method is simple aeration, which converts the soluble forms to insoluble precipitates that you can filter out. However, manganese oxidation is significantly slower than iron, so it often requires larger tanks or chemical assistance.
What are the primary chemical or catalytic methods for that?
First, you have manganese greensand, which uses a special medium that acts as a catalyst for oxidation. It's regenerated using potassium permanganate. Second, chlorine dosing. This is highly effective at oxidizing iron and manganese. But a big caution here. If your source water has high organic content, combining chlorine with it can create dangerous disinfection byproducts, or DBPs like trihalomethanes. And third, you have berm media, which is a granular filter material that acts as an active catalyst and requires no chemical regeneration, just a high-velocity backwash.
Our final advanced treatment topic, defluoridation. Fluoride above 1.5 mg/L is toxic. It causes dental fluorosis and the irreversible bone condition, skeletal fluorosis.
The complexity of defluoridation often requires methods that are adaptable to rural environments. You have absorption by activated alumina, AA. AA is highly selective to fluoride and can be regenerated. You also have ion exchange adsorption, but its high cost and complex regeneration make it pretty impractical for small village service. Which brings us to the Nalgonda technique.
This one is a high-yield exam topic because of its widespread practical application, especially in India.
Exactly. It's simple and economical. It uses aluminum salt, or alum, combined with lime or sodium carbonate.
Why is the Nalgonda technique so well regarded for decentralized use?
It's a multi-benefit process. The lime ensures there's enough alkalinity for the alum to work efficiently, forming a massive, quick-settling precipitate. This precipitate physically sweeps out the fluoride ions. But at the same time, it acts as a superior coagulant, removing turbidity, color, and bacteria. Uses widely available chemicals, simple equipment, and doesn't require complex disposal schemes. It's a true low-cost, multi-barrier approach.
Right. And finally, reverse osmosis can do it, but it's rarely justified just for defluoridation because the costs are just too high.
That's right. So that brings us to our final summary section, Unit V water distribution systems.
We're at the finish line, where the system meets the consumer. The function and requirements are simple but demanding. Transport the treated water reliably, maintain adequate pressure, maintain purity, and be economical and easy to maintain.
Let's focus on the four main layouts of distribution systems. The engineering choice here really defines the reliability of an entire city's supply.
Okay, what's first?
First is the dead end or tree system. It's the simplest, cheapest, and easiest to calculate. But the disadvantages are severe. Water stagnates at the dead ends, causing quality issues, and any break isolates the entire downstream area. That's a huge problem for firefighting.
So what's the alternative?
The gridiron pattern. It's an interconnected network with pipes forming loops. The advantages are no stagnation, continuous supply even during repairs because water can flow from multiple directions, and superior firefighting capacity. The disadvantages are higher cost and more complex hydraulic calculations.
Then you have the ring system and the radial system.
The ring system is just a variation of the gridiron, often used around big city blocks. The radial system divides the city into zones, each fed by a local reservoir. Water flows from the reservoir, which makes pressure calculation easier. It's excellent for hilly or large, sprawling areas.
And the system of distribution, the flow type, defines how the pressure is generated. There are 3 methods based on cost and reliability.
First, the gravity system. The source is elevated naturally like a mountain lake. It's the most reliable and has the lowest operational cost zero pumping. Ideal, but totally dependent on geography. Second is the pumping system, or direct pumping. Water is pumped directly into the mains to maintain constant pressure. This requires strict control and expensive standby units in case of a pump failure. And third, the dual system, or combined system. This is the most common and efficient solution. Water is pumped up to elevated storage tanks, and then gravity distributes the water to the consumers.
And that lets the pumps run efficiently during off-peak hours, right?
Exactly. You store energy in the form of potential head in the tanks, and it provides reliable pressure even when the pumps are off.
Finally, maintenance of pipes, the unglamorous but necessary part.
This includes preventative measures like leak detection, constant corrosion control, routine flushing of lines, and rigorous record-keeping of repairs to spot failing infrastructure trends before they become catastrophic.
All right, that was a comprehensive tour. We covered everything from the 50-year design life of a dam all the way down to the microscopic HOCl species that's killing bacteria.
It was. And to succeed in the OEN 351 exam, you really have to synthesize this material. You have to understand the crucial engineering trade-offs.
Like, why is concrete preferred over steel for a major aqueduct? Well, because the long-term operational savings from zero tuberculation outweigh the high initial cost and difficulty of repair. Or, why is a lower pH better for disinfection? Because the highly effective HOCl species is favored at a slightly acidic pH.
And you have to master those numerical methods. Practice the population forecasting problems. Make sure you can state and apply the various fire demand formulas, Quechling's, Freeman's, and so on. The comparative tables, SSF versus RSF, lime soda versus zeolite, dead end versus gridiron. That's where you will demonstrate true mastery of the selection criteria and the underlying engineering principles.
So we'll leave you with the final provocative thought we touched on earlier, one that integrates this whole system. We invest so heavily in advanced technologies in Units 3 and 4. RO plants, high-efficiency filters, complex chemical dosing, all of it is aimed at producing water purity measured in parts per billion. And yet, back in Unit 1, we budget for 15% of that perfectly treated supply to be lost as losses and wastes due to infrastructure failure in Unit 5. As a modern engineer, how do you reconcile the increasing scientific complexity required for treatment with the fundamental non-technical challenge of maintaining the physical integrity and public accountability of a distribution system that loses 1 out of every 6 liters of water?
Use this deep dive as your detailed study guide. Good luck with your preparation for OEN 351, and keep that focus tight on the application of the knowledge.